4 wheels, an engine and a need for speed. The fundamentals in 1950 are what makes Formula One as we know it today. Though as we look back, the cars from the first ever Formula One in 1950 are hardly recognisable from the cars we see today. So why is this? With a massive breakthrough in technology, polymers have now become an integral part of F1, probably more than you think so. From chassis to steering, engine to tyres, the helmets to the clothes the teams wear, F1 is quite literally surrounded by polymers. How polymers have revolutionised Formula One. So what is a polymer? A polymer is a material made of a long chain of repeating units. These repeating units are called monomers. Polymers fall into 2 categories, naturally occurring polymers, or polymers that have to be synthesised by scientists or engineers. The properties of the polymer is made up by the properties of the monomer, for example being waterproof. The process by which we join these monomers together is called polymerization, and this can be done in a variety of ways. Though today I'll only really be talking about free radical polymerization. Originally, F1 tyres were actually made out of a cotton-based material, and all the tyres had grooves in them. By 1958, these were replaced with a nylon fabric, a polymer that made the tyres significantly lighter. The 1960s, among other things, brought the use of synthetic rubbers, and by 1971 we had the first introduction of slicks. Here is where we really start to see some similarities to the tyres we know today. Now for a bit of background chemistry. So polymers are actually able to exist in 2 different states, the glassy state and the rubbery state. The glassy state is when the rubber is at its most rigid form, as the individual polymer chains are essentially fixed. There is insufficient energy for them to move. However, at higher temperatures, the polymer chains have significantly more energy to move, making the overall structure soft and pliable. This is the rubbery state. The temperature at which this transition occurs is known as the glass transition temperature. Each polymer will have a different glass transition temperature, and that's actually dependent on how high or low modulus the compound is. The higher the modulus, the stiffer the compound. I'll talk about this in more detail later on in the presentation, but for the time being, here's a diagram to kind of give you an idea of what's going on. Now, the exact composition of Pirelli's F1 tyres are not known to the public, but ultimately the basic structure will most likely come down to a mixture of different synthetic polymers and natural rubbers with steel reinforcements. Due to this, F1 tyres are able to withstand much larger forces than any normal road tyre. F1 tyres are quite literally designed to deteriorate whilst they're being used on the track to give them the grip they need. So how do the drivers achieve this? Well, often before a race, drivers will do what is called a heat cycle, which is essentially bringing their tyres up to the optimum working temperature and prepping them for the race. In this short clip, we can see some of the drivers in the USA 2005 Grand Prix doing this heat cycle. From going side to side, they are warming their tyres up. This is where the idea of the glass transition temperature comes back. At this temperature, the tyres become a lot softer and are almost viscous and sticky. So when these softened tyres are run over the rough track surface, they're actually able to squeeze into the surface texture. This is essentially what causes the grip. However, over the course of the race, the polymer chains will distort due to the excessive heating. After each heat cycle, most of the polymer chains will spring back to their original form, but some of them will have enough energy to break bonds and distort its shape. Eventually, enough polymers will be distorted that it completely changes the rubber's chemical structure and properties. The rubber will become harder, have a higher glass transition state, and therefore become less grippy. This is why cars are forced to pit at least once during a race. Otherwise, drivers risk losing too much speed due to lack of grip, a puncture, or a full blowout. Now we can move on to an area which arguably has the most noticeable change since 1950, the chassis. A massive push towards lowering air resistance and increasing speed meant incredible aerodynamic and material changes. In terms of polymers, well, gone are the days of chassis built from steel and aluminium, and now in with the carbon fibre. First introduced into Formula One in 1981, carbon fibre is now one of the most abundant materials found within an F1 car, especially the chassis. Believe it or not, all organic materials used to make carbon fibres actually originate from organic molecules which react to form organic polymers. About 90% of these come from the polyacrylonitrile method. So firstly, we have to make our monomer from propene and ammonia to make acrylonitrile. After the addition of a catalyst, known as an initiator, all the individual acrylonitrile monomers will join together to form our polymer, polyacrylonitrile. This happens by a process called free radical polymerization. This is a form of polymerization that, as the name suggests, involves free radicals as the initiator. From there, these long polymer chains are then mixed with other chemicals and spun into fibres which are then washed and stretched. In doing so, you can change the properties of the polymer. Scientists can essentially pick and choose which properties they want their polymer to have and add it. From there, the fibres are spread out and heated from 200 to 300 degrees Celsius in the presence of air to oxidise the fibres. In doing this, we are stabilising the polymer. The nitrogen atoms are losing their energetically unstable triple bond and instead are ring closing with a neighbouring carbon atom. The next step is carbonization, where the stabilised fibres are heated from 600 to 1300 degrees Celsius without oxygen this time. The carbon fibres vibrate, and some of the chemical bonds to non-carbon atoms break, releasing them, forming tightly bonded carbon crystals. The higher the temperature we heat the fibres to, the more non-carbon atoms we are removing and the more strong carbon-carbon bonds we are forming. The fibres become lighter, have a lower volume, and the strength to volume ratio massively increases. We come back to the modulus. The higher the temperature, the higher the modulus, the stiffer the material, and when it's made into composites, it's much stronger. In Formula 1, cars are made out of high to ultra-high modulus carbon fibre. From there, the carbon fibres are turned into composite materials, where different resins are applied to thin sheets of fibres, again giving them different properties. In F1, pre-impregnated epoxy resins are used, with an aluminium honeycomb layer, sandwiched between two layers of carbon fibre. This makes cars able to withstand incredible forces, whilst also remaining amazingly light. So what's in store for the future of Formula 1? When Formula 1 first began, normally teams would push towards making their cars faster every year, but after the 2008 Make Cars Green campaign was announced by the FIA themselves, FIA Director David Ward made a statement about making more fuel-efficient vehicles to help the fight against global warming and climate change. A fight to a green F1 began. In 2019, Liberty Media calculated the total carbon emissions over a race season. Just under 260,000 tonnes of CO2 was generated, with the vast majority being in logistics. In November that year, the FIA announced a net zero carbon emissions by 2030, and naturally the most concerning area was the logistics. Now, the logistics sector encompasses all air, sea and road transport for the teams and their equipment between races. There's been a massive push towards low-carbon transport after the implementation of climate policy, and an even bigger push towards biofuels being used. At the moment, biofuel requires poorly degradable synthetic polymers, which are not only detrimental to health, but also the environment. In future, it is hoped the research today into biopolymers and bio-based polymers, such as polysaccharides and biopolyesters, will be able to replace the current polymers used in biofuel processing. These new biofuels are usually derived from renewable biological sources such as plants and will increase the processing sustainability for the fuel itself and for F1. So, overall, polymers will continue to be developed in almost every aspect, but the newest and most exciting area of sustainability and the heightening popularity of Formula E will most likely be the direction of improvement for the future. Thank you.